Hi, in this section we are learning on how to do a testing a claim about proportions. The goal is to conduct a formal hypothesis test of a claim about a population proportion P and recall that the best point estimate for the proportion should be the p hat equal x over n, where x is the number of the individuals in the samples and n is just the sample size. We are doing the testing using the p-value methods or the critical value methods. Before doing the testing, we have to check the requirements. Make sure that it should be a simple random sample. And then the conditions for a binomial distribution are satisfied. That means there is a fixed number of independent trials having constant probabilities and each trial has two outcomes. It's either success or failure. And then the condition np0 has to be bigger than or equal to 5, and then nq0 is also bigger than or equal to 5. And they have to meet these two requirements so that the binomial distribution can be approximated by a normal distributions, with the mean mu equal np0 and the sigma or the standard deviation is the square root of np0 q0. And q0 is just a complement of p0 or 1 minus p0. So here is the procedure for doing the claim. There are two parts. The first one we are using the p-value methods, and the second one we are using the critical value methods. Now the first step is before doing any claim, we must determine the null and the alternative hypothesis. It's very important that you have a right null and alternative hypothesis, because at the end we are making the conclusion whether we should reject or we fail to reject the null hypothesis. And then we can construct them in the following three ways: the two tails, the left tails, or the right tail. So for the null hypothesis, the proportion is equal to some claim value is always equal to something, right? And then the alternative hypothesis p0, for the two tails, p has to be different, the proportion is different from the claim value. The left tail is less than that claim value, which is pointing to the left, and then the right tail is bigger than the claim value, or it's pointing to the right. And p0 again is just the sum value of the population proportion. And the null hypothesis always include the equal sign. You can see here equal, equal, and equal here. And then the next step is we select a level of significant alpha, and this will depend on the seriousness of making a type 1 error. And the common choice for alpha is 0.05, and usually we are given this value in the problem. And then to do the p-value, we must compute the test statistic. And the test statistic for the normal z should be the point estimate minus p0, which is the claim value here, over the square root of p0 q0 over n. And once you get the test statistic, and then we can use the table A2 or technology to determine the p-value. So the test statistic will be here, either here for the left tail, the right tail, or the two tails. And then all you do now to find a p-value for the left tails, we either find one of the region here, which is the area, and then multiply that by 2 because the graph is symmetric. And then for the left tail, we just find the value from very far from the left up to the test statistic for the area under the curve for the p-value. And for the right tail, just the area to the right of that statistic. Remember, the p-value is just the probability value, which is the area under the curve. And then for the TI-83 or 84, we can use the normal CDF function. This is the normal distribution, and CDF is just a cumulative area to the left. Okay. And then we make the conclusions. If the p-value, which is the area here, if that is less than the alpha, we reject the null hypothesis. If it's bigger than alpha, we fail to reject or we do not reject the null hypothesis. Now for the critical values, we do the same thing up to the test statistic. Now, instead of finding the p-value, we now use the table A2 to find the critical values. So this is the critical value, z alpha for the right tail, or minus z alpha for the left tail, or z alpha over 2, because we have two tails, so the alpha now is divided by 2. Alpha over 2 for the right, and then another alpha over 2 for the left. So together, alpha over 2 and alpha over 2, they give you 1 alpha. Two tail, left tail, and right tail. And then we compare the critical value to the test statistic. If that for the two tails, if the test statistic z0, which is this guy here, if that is less than or is inside the critical region, the left one or the right one, then we reject the null hypothesis. And then for the left tail, if it's less than this minus z alpha, then we also reject the hypothesis. Or it's bigger than z alpha, then we also reject the hypothesis. In other words, for the critical value methods, if the test statistic is inside the critical region, then we reject the null hypothesis. And then when checking the requirements np0 bigger than or equal to 5 and nq0 bigger than or equal to 5 for a small sample size, it usually won't pass the conditions. And we need to use the binomial distribution instead of the normal distribution. If the two requirements here are not satisfied, then we have to use the binomial, because we cannot use the approximation of the normal distribution if these two requirements are not good. Alright, let's try one example here. The Genetics and IVF Institute conducted a clinical trial of the white short method, designed to increase the probability of conceiving a boy. As of this writing, 291 babies were born to a parent using the white short method, and then 239 of them were the boys. We are using the 0.01 digit alpha significant level to test the claim that this one, the white short method, is effective in increasing the likelihood that a baby will be a boy. Okay, so before doing anything, we have to check the requirements. Now, this is a sample, random sample, because we conduct the clinical trial randomly from this survey here. And then this is also a binomial distribution, because why? Either you get a boy, success of getting a boy, or failures of getting a boy. So there are two cases, success or failure. So this is a binomial distribution. And then now we know that the proportion that we get the boy is p0, and p0 is just that proportion is 291 babies. This is n, this is total n, so 239 out of 291. So 239 out of 291, this proportion now is 0.821, and multiply that by n, which give me bigger than 5, and also multiply to 1 minus p0 is also bigger than 5. This is a typo here. So yes, we are good for the requirements. Okay, so now let's use the p-value methods. The original claim. So the claim here is that the white short method is effective. This is effective. The effective means that the probability of getting a boy is bigger than 50%, because when you give birth to a baby, you either get a boy or a girl. So each has a 50% chance of getting a boy or a girl, which is p equals 0.5 is the one without any changing, no effect, no change, without doing anything. Then we should have p equals 0. So p equals 0.5 is the one that has the equal sign, and the one has no effect, no changing, so it should be the null hypothesis. And the one that we claim now is that If the methods, white short methods, is effective, that means the probability of getting a boy is bigger than 50%, or P is now greater than 0.5. So this becomes the alternative hypothesis because it does not involve the equalities. Okay, so we are doing the testing for this hypothesis here. This is the right tail test because we are bigger than 0.5 and it's pointing to the right, so it should be a right tail test. And the level of significant level alpha 0.01 is given here. And how do I find the test statistic? This is the test statistic. Go back to here. This is the test statistic. Right here. P hat, this is the point estimate, minus P naught, this is the claim value, and then so on. Now, there should be a typo here. This is P hat, this is the point estimate. And then this is also the P hat here. So Z naught, P hat minus P naught. P naught is the claim value. We claim that to be 0.5, right? P naught is 0.5. So this is P hat. Let me write P hat here. Okay. So it should be the P hat right here. And then it should be P hat right here. There's a typo. Right. So P hat. And then, yeah, plug in the value of P hat. And P naught is the claim value 0.5. And then 1 minus 0.5. The sample size 291. The total 291. And then that should give me Z naught, or the test statistic, to be 10.952. We are doing the right tail test. So this is Z naught now is 10.952. And we are looking for the area to the right, because this is the right tail test, to find a p-value. Now, how do I do that? Well, to find a p-value using the TI-83, we hit the second verse and we choose a normal CDF. And because we are looking for the P of Z is bigger than 10.952, that means we go from the normal CDF, the lower bound, which is 10.952, and we want to go all the way to the right to infinity. But there's no infinity symbol in the TI-83 or 84. So for the upper bound, I just say that's a very large number, 10 to the 99 power. Or you can just put like 100,000, something like that. Some large number. So the lower bound, the upper bound, and then we hit enter. And it should give me the p-value. This is very, very, very small value, to the power of minus 28. And this is, of course, is less than the alpha, which is the 0.01. And if the p-value is less than the alpha, we reject the null hypothesis. Okay, so in this case, yes, I do reject it, the null hypothesis. Okay, let's me try the calculator here for you to see. So we go from second first, and we choose the normal CDF. This is the area to the left. No, sorry, this is not a table A2 or A3. We are just using this one, the lower bound, which is the lower bound in this case, which is Z naught, or 10.952. So 10, okay, 10.952. And then the upper bound is very large number. We go all the way to the right. So let's do 10 to the 99, just a huge number. And then we give the mean to be 0. Standard deviation is to be 1. This is the standard normal Z. And then we paste that into the commands of the normal CDF. So the normal CDF, lower bounds, the upper bounds, the mean, standard deviation, close the parenthesis here, then click enter, and it gives me the value of very small value. So it should be less than 0.01, which is alpha, so we do reject the null hypothesis in this case. And then for the critical value methods, okay, let's go back to what happened if I use the table A2 to find the normal CDF here. Can we do that? And why I did not use the table A2 in this case to find the area to the right? Now let's try that here. Well, this is the z-score table A2. Now we have the z-score of 10.952, and unfortunately here the table z-score only gives you up to 3.5, so there's no value for 10 and up, so it's very difficult for us to use table A2 in this case, because we do end up with a high z-score. So in this case we have to use a TI-83 to help you, or 84 to help you. And then for the critical value methods, so after finding the test statistic, instead of finding the p-value, we can now find the critical value instead of the p-value. And from chapter 7, how do I find the critical value? We are given the alpha is 0.01, and this is the right-hand test, so alpha is the whole thing to the right, 0.01. That means this is the whole area 0.01, so the one to the left of that should be 1 minus 0.01. And how do I find the critical value here? Well, again, you can find the we are given the area. Now you just want to find the z-score, so we can find it. You can use the inverse num function. So go back to TI-83-84 second verse, and then use the inverse num. So clear second verse. Instead of finding the normal CDF, which is the area, now we find the inverse of that because we are given the area. So I use the inverse num, and then the area, which is this is the area to the left. It's give you the area to the left from this here. This commands here. So I do 1 minus 0.01, and then I paste this. So the inverse num function takes the input of the area to the left of that z-score, and that should give me 2.33. And can we do that using table A2? Okay, let's try. The area of 1.1 minus 0.01. Okay, let's check that here. So you can see here, this is 0.89. This is true, 0.89, which is this guy to the left of the z-score. So let's go back to the table. 0.9. We have to find the 0.99, which is the area. Yeah, we have a lot of 991316 and so on. Now this is not a good way for you to find the inverse z-score given 0.99, because there's too many here and it's not very accurate to use the table as well. So in this case also we do need to use the TI-83 or 84 to help you to find the inverse num to be 2.33. You go back here, 2.33, 2.3 is here. So 33 is this column, right? 0.03, 33 right here. So yeah, 0.9901. So it's take 4 decimal places. We are 0.99. So make sure that between 9901, 9904, 9906, 09, we have to pick the one that is very close to 0.99, which is 0.9901. So this is the best number for 0.99, and that should give you 233 in this case. 2, 3, 2.3 and then 0.3 more give you 0.33, which is this guy. Well, we can do that from here, but it's time consuming and we have to look through all the number. And it's very easy to just use the TI-83 or 84 in this case. Now, once you get the critical value, this is the critical value, Z alpha 2.33, and then Z naught is the test statistic we got here, 10.952, and that value is way beyond the Z alpha or the critical value, so it is inside the critical region. If it's inside the critical region, now we compare for the right tail. If that is inside the critical region, Z naught is inside or bigger than Z alpha, we do reject the null hypothesis. Okay, so we reject the null hypothesis using the p-value. And the same way with the critical value, we also reject the null hypothesis. So the two methods, they do give you the same consistent conclusion, which is rejecting the null hypothesis. Now, if we reject the null hypothesis, meaning that we are saying that p equals 0.5, which is the probability of getting a boy and a girl with 50% is not true. If it's not true, then the other one should be okay, right? Or we can say that there's sufficient evidence to support the claim that the Weierstrass method is effective, because you don't because you reject the null hypothesis. That means we prefer this one. This should be correct one, and that means it's bigger than 50%, or it should be effective. Okay. Now, we have gone to a lot of procedure to find the p-value or the critical value. But now we can just use the TI-83 or 84 to do the testing. It's very easy and without doing anything. Okay, so what we do now is we use the one proportion z-test command to perform the z-test to compare a population proportion to a hypothesis values. And this test is valid only for the requirements of binomial distribution is satisfied right here. Now we hit the stats and go to the test menu, and then choose the one proportion z-test, and then enter the below the screen information here. Because we know that the p-naught is 0.5, which is the one that you saw here, p-naught, which is 0.5, right? The claim value. And then we have the x to be 239 babies to be a boy, and then the sample n in 291. This is the right tail test, so it's bigger than p-naught, and we hit the calculate button here, so that it gives you all the values. This is the test statistic. This is the p-value, which is the one we got earlier. This is the p-hat or the point estimates. Okay, so how do I do that? I go to second verse, stats, go out, start, and then arrow to the right, calculate, and then choose the not the stars, not the calculate, but the testing, and then go to one proportion z-test here, and then just enter the data that I show you here, and then hit the calculate to display the data, and we do got the same thing, right? The p-value we got earlier is 3.010 to the minus 28, and it's very close to here, 2.9, which is 3 to the 10 to the minus 28. Okay, one more example. Now in the 2006, 10.5% of all the live births in the United States was to mothers under 20 years of age. A sociologist claims that this percentage is decreasing, so they are claiming that this decreasing. So she conducts a simple random sample of 34 births and finds that 3 of them were to be mothers less than 20 years of age, and tests a sociologist claim as this level of significance. Okay, so we are given that the sample size is 34, the x is 3, and the alpha. Now we have to check the requirement. This is a simple random sample. Yes, this is a simple random sample. This is a binomial because either that we have the live birth or is not living, right? So 2 cases. And then the next one, we are testing for the NP0 and NQ0. Now we are given a claim that 10.5 of all the live births in the United States. So this is 10.5. This is the claim value for the proportion or P0. So that is 0.105. And n times that is 3.57, which is less than 5 because we need to be bigger than or equal to 5. So we fail the requirements to use the normal distribution to approximate the binomial, and that's why in this case we have to use the binomial distribution but not the normal distributions. Now the sociologists claim that it is decreasing, so the proportion is decreasing in this case because it's decreasing is less than the one in the beginning without any changing, no effect, no difference, then p equals 0.105, and this involves the equal sign or the null hypothesis. And the one that's without the equal sign decreasing, it should be the left tails because this is pointing to the left. Now we have 3 successes in 34 trial. That means 3 of them was to be more or less than 20 years of age, and the rest are not. So we have 3 successes. We have success and failure. So that is the binomial distribution. And then we are looking for decreasing. Decreasing, that means it's less than or equal to 3. That means we are looking for the p-value, which is the probability of x to be less than or equal to 3, because 3 is the number of successes. So less than or equal to 3 represent for the decreasing. So we have to use the binomial CDF. We cannot use the normal CDF in this case because this is not a normal distribution. We cannot approximate that. We have to use the binomial. Then the TI-83 or 84, they also have the commands of binomials by binomial CDF, and it takes 3 inputs. The first one is the number of the trials. This is the claim value of P0, the proportions, and then X is the number of success here. So how do I do that? Second verse, and then we go on the distribution again and select the binomial CDF. So go here, axis, second verse, and then we use to we go to binomial CDF right here, and then enter, and then enter the number of trial, p value, the proportion, the claim proportion, x value, which is what I got here. This is p0, this is number of trials, this is x value, and then we paste that to the syntax here, and then we got the p-value of 0.51, and this of course is bigger than alpha, which is 0.01, and if it's bigger than alpha, we do not reject. If we do not reject the null hypothesis, that means we don't have enough evidence or sufficient, or there is insufficient evidence to conclude that the percentage of the live birth in the US to the mothers under the age of 20 was decreased. So we don't have, if we fail to reject the null hypothesis here, that means we don't have enough evidence to support for the alternative hypothesis. That means we don't have enough data or evidence to support the claim that the sociologist is making. Okay, and that is the end for this section, and thanks for watching.